Right. So very happy to introduce my friend Yogarshi. He's a PhD student at University of Maryland at College Park, advised by Professor Merin Karpua. He received an undergraduate degree from Indian Institute of Technology at Kharagpur. And yeah, I'm a big fan of Yogarshi's research. Let's see if I can summarize it in a few sentences. So he has done work in semantics, multilingual NLP, machine translation, and his current research focuses on contrasting meanings of text in various languages using the simple idea of textual entailment, for which he received a recent best paper. And I think we are going to hear a bit of that. So.
Is this audible? Okay, really pleased to be here. I did not expect such a sizable audience. Hopefully I can do justice to this. So thanks Rajarshi for the kind introduction. I'm Yogarshi. I'm a PhD student at the University of Maryland. And today I'm basically going to be talking about two different projects that I've been working on that both have to do with this idea of Hypernym E detection. And I'll be talking about it in two different segments. I want to make this informal, so if you have any questions in between, please feel free to interrupt. Especially in the second half, since it's more of a work in progress kind of thing. So I'd really like to get good feedback. Okay, so let's start with looking at what this idea of Hypernym E means. So Hypernym E is basically identifying whether a given word is a specific type of the other word. So in this example, we want to identify if game is a hypernym of chess. And the answer is yes, because chess is a specific type of game. So in more computer science terminology, you can think of this as having an is-a relationship in object-oriented settings and so on. But this problem has been very, very well studied since ages. What I'm going to be talking about is not this exact problem, but two different scenarios in which this problem can be modified. And the first of this is what happens if instead of giving two words in the same language, I give you one word in English and the other word in, say, French. Can you reliably detect whether the two words have a hypernym E relationship between them? Or on the other hand, what happens if I, instead of giving you just the two words, give you two sentences? And this is an interesting scenario because if you look at these pair of sentences and I ask you the question, is game a hypernym of chess? Then the answer would be yes, because the meaning of game and chess still imply that chess is a specific type of game. On the other hand, if I use this other sentence, where the meaning of the game is quite different, meaning of the word game is quite different, then there's no longer a hypernym E relationship between these two words, because chess is not a type of game as the word game has been used here, right? So this discrepancy here highlights the need to study hypernym E in context-aware settings, settings where the meanings of the word are influenced by the sentences in which they are used. All right? So basically, the two projects I'm going to be talking about is Hypernym E detection in context, which is a paper that we presented at StarSem in ACL this year. And the second work is doing Hypernym E detection in cross-lingual settings, which we published in NACL last year. But I'm really going to be talking about work in progress that I'm doing with collaborators from the University of Pennsylvania. All right, so let's dig into the first of these two problems and see what we can do with Hypernym E detection in context. So just to formally define the problem, what we are given as input in this setting is two words. So again, going back to the chess and game example, along with two specific sentences in which these two words have been used. And the task then is a simple, straightforward binary classification task where the example is positive if game is a hypernym of chess in the given context, and it's negative otherwise. Okay? So that's just the straight up definition of the task. There are two pieces of input, the words and the sentences in which the words have been used. All right, so why do you want to study this task in context? And there are like multiple reasons. The first is that there's an obvious benefit in terms of downstream tasks, because any downstream NLP task which involves identifying semantic relations between words is usually going to have words used in specific contexts. You're going to have sentences in tasks like question answering, where you have to reason between words, or things like textual inference, where you have to identify whether the meaning of one sentence entails the other sentence. And in all these tasks, you're going to have words used in specific settings and not just words standing on their own. So that's one thing. The other thing is more based on this idea of hypernymy detection out of context. So when you're doing that, if you go back to the previous example about chess and game, you, as an annotator, you have to think about what are the different possible senses of the word game. And does hypernymy hold in one of these senses, or like in all of these senses? So there's a lot of burden on the annotator to do like thinking about what the words mean. In our setting, what we can do is effectively ground the meaning of words in specific sentences. Since I'm giving you two words and two very specific sentences in which they have been used, the meaning of the words is automatically grounded in sentences that we use. And the assumption here is that we are not dealing with word senses and so on. We are assuming something like there's just one word sense per sentence. Like every word in its occurrence is unique. OK, so I'm not going to be talking about a lot of previous work, but I do want to give mention to this paper, which was, again, sort of a spiritual predecessor by Vered Schwartz and Ido Dagan. What they're trying to do is they've built a data set for very fine-grained lexical inference, which consists of a lot of different semantic relationships, 6 different semantic relationships, and about 3,000 examples. But the focus of our work is not on all of these different relationships. We are just going to be focusing on the specific problem of hypernymy. So we wanted to go beyond what this work has done. I'm not going to be talking about experiments that we did with this data set, but if you want, there are more details in the paper.
What are the relation types?
So things like, so entailment is one. They also have negation, alternation, unrelated things between words in sentences. So again, the setting is very similar to ours, but that there are more relationships there. But the focus is not on one or the other relationship. We are focusing specifically on hypernymy. OK, so in this work, what we are trying to do is, first, we are going to construct a data set automatically using WordNet. And I'll talk about this in a bit. This data set consists of hypernym pairs in context, so we can use it for our experiments. What we are going to do is use this data set to compare different ways of representing the context. So like, how can you represent different sentences? And how does this help in your in the task of hypernymy detection in context? We can also analyze how these different representations behave when it comes to identifying how sensitive the models are to context, or whether they capture directionality correctly. And what I mean by directionality is this idea that game is a hypernym of chess, but the reverse is not true. So it's really an asymmetric relationship that we are trying to capture, as opposed to, say, synonymy, which is a more symmetric relationship. So car means automobile, and automobile means car. And that way it's symmetric, but that's not true for hypernymy. And sort of like our analysis is going to tell us that this is a really challenging task, maybe because of the models we considered, which probably means that we need better models of representing context. It's sort of a spoiler alert. OK, so let's get into the details. I'm going to be talking about the way we construct our data set first. But before that, let's take a moment to think about what are some characteristics that you would like from a data set that you're building for detecting hypernymy in context. And the first thing that you want is, by definition, you want the data set to enable you to analyze how different models behave when you change the context in which the sentences are used. So this is true by definition of the task that we are interested in. The second thing that we want to do goes back to the other point that I made. We want to differentiate between hypernymy and semantic similarity. So game is a hypernym of chess, but checkers is not a hypernym of chess. Even though both of them are very similar, they're very related to each other. And like I mentioned earlier, one is an asymmetric relationship, the other is a symmetric relationship. So we want our models and our data set to help us discriminate these two different things. And finally, we obviously want the data set to be large enough so that we can train reliable supervised models on. OK? So just a brief refresher on what, since our data set is extracted from WordNet, WordNet is basically a hierarchy of words organized into sets known as synsets, where all the synonyms are put together in a single synset. So just to take a particular example, this is a synset corresponding to the word study or sketch, as in the study of a drawing. The key point about WordNet that I want to highlight is the fact that a lot of these synsets in WordNet are accompanied by example sentences. And the idea behind our data set is to use these example sentences to construct the data set. So the way we do that, I'm just going to walk you through an example. Here are two different meanings of the word study with an example sentence. Each of these is going to have their own hypernym. So the word on the left, which says study, is a kind of a room. So this is the kind of a room where you go and like do your work or like office work or whatever. On the other hand, the word on the right is a word which means a kind of a drawing. So these are two completely different senses with their own hypernyms. And so by following the Hypernym E relationship, you can get positive examples for our data set. And each positive example consists of a pair of words and a pair of sentences in which these words have been used. So like just going back to the definition of the task, this is how we want our positive examples to look like. The first way in which we construct the negative examples is by permuting the different senses together. And what I mean by this is instead of associating room with study here and drawing with study here, I'm going to pair them in like a cross product way where I'm pairing room with the other meaning of the word study. And so what I get out of this is this kind of an example where the word pair remains the same, but the sentences that I'm using are different. And in this setting, the word drawing is no longer a hypernym of study because the meaning of the word study corresponds to room, whereas the meaning of the word drawing does not have anything to do with the room. So that's the first way in which you can get negative examples. The second way to get negative examples is to flip the positive examples. So by flipping those green solid arrows at the top, you get the red dashed arrows. And what you get from there is the sort of negative example where study is not a hypernym of room because the relationship is actually the other way around. So room is a hypernym of study. So we want to also differentiate between these, like I mentioned earlier. Okay. Any questions on the dataset creation process? Slightly can be confusing, but yeah. Yes, it is transitive. So if C is a hypernym of B and B is a hypernym of A, C is going to be a hypernym of A. Yes. What do you mean? Mm-hmm. Yeah. So what I want to say is that this, like the dataset generation process, is as correct as you can assume WordNet to be. So WordNet has inherent flaws. So what you're trying to do is like just add a layer of manual annotation on top of this to make sure there's like no false negatives that you mentioned. Yeah. Oh, okay. Sure. Yeah. No question.
So when you're creating the dataset, are you also making sure that the word that you're focused on is going to remain as is? What I mean to ask is basically, how do you know that study is the word that you would be interested in this sentence when you're doing the hypernym detection later on?
Right. So when we construct the data set, we like sort of underline the word so that our model knows what the input is because it's the word that we are looking at is our input. So that's something that's known to our model.
That means that your studies from here on are going to carry over old biases from WordNet.
Yes, they are going to carry over, and that's a very good point because WordNet has a lot of biases. But yes, they have all the biases that WordNet has. Right?
Basically, in this case, we mean that study is more of a drawing.
No, what I mean is that study is a type of drawing. It's a specific type of drawing.
But in some other cases, drawing may be some other kind of study.
Yeah. So that's what we are trying to differentiate here. Like, so drawing may be a different kind of drawing. It need not be a study. But like study as used here is used to refer to drawing. So all studies are drawings, but not all drawings are studies. Yeah. All right. So that's sort of like the whole picture of our data set. And by virtue of like construction, oh, question. Right. Right, but WordNet only has relationships between words and like at the word level. The task that we are trying to do is at a word in context level. Yeah. Yeah, sorry, WordNet has a sense level. I meant that. So synth sets are where words are grouped into synonyms are grouped into the same set. Cool. So by virtue of like construction, data set is sort of satisfying the characteristics that we wanted to. And by feeding it with like a large enough input vocabulary, you can get a large enough data set to work with supervised models. So the next question is, what can you do with this data set? Can you test the effectiveness of different ways of representing context on this task? So just a brief refresher on how Hypernym E detection typically works in supervised settings. You start out with like word representations for the two words. So for example, if you're trying to identify Hypernym E between chess and game, you start out with the word embeddings for these two words. And typically you extract some sort of features on top of these word representations. So things like dot product, differences, concatenation. There's a bunch of things you can do. And then you throw that into a classifier and predict what happens. But the specific model for Hypernym E detection is one that we are going to use from past work. I'm not going to go into a lot of details of this model, but basically like fixes a lot of flaws that were inherent in previous models. I can talk about this in the end if people are interested, but it's really just treating this model as a black box for now. You can imagine it to be like a classifier. But the key point is that this model takes in as an input a word, whereas for our task, what we are really interested in is the meaning of the word in a given context. So the question is, how do you bridge this gap from word representations to context representations? Word in context representations. And the way we do that is we form a representation of the context, and then we take an element-wise product between the word and the context to effectively get the representation of the word in context. And the idea behind this is that you want the context to sort of act like a mask, where you're trying to upweight the more important dimensions and downweight the less important dimensions in the original word representation. Yes?
Do you have a gate? Like, do you learn a gate?
No, so there's no learning. It's just like a straight up not vector product between elements. Yeah. Yes? Yes, so that's the next question. So how do you learn representations of this context? So what we are going to do is we're going to look at two methods to learn the representation for the context. And sort of like two complementary approaches in some ways. The first one is based on this idea that taking the average of the words in a sentence is usually a very frustratingly good way to get representations for the sentence. So what I mean there is, suppose you're trying to represent this sentence, the river bank. Each of the words in this sentence will have their own embeddings. You can take the mean of the embeddings to get one representation for the entire sentence. But since we are interested in Hypernym E, not all words contribute equally to the final semantic relationships. So we go a step ahead and take the max and the min of the word embedding. So we take a dimension-wise max, a dimension-wise min, and just like trying to capture more general properties than what the mean does. So this gives you three different representations for the context. So if your original word representations were d-dimensional, you end up with like a 3D representation for the context. So we just concatenate these three representations together. So that's the first way, based on just combining word type representations by simple operations. I'm going to call this approach the pooling approach, sort of inspired by the pooling process that goes on in CNNs. The second one is based on RNN composition. So we're going to do something a little more advanced, where we are going to say we are going to embed words and contexts into the same space. And the way we do that is we use this particular model called context to vec. And what this model tries to do is it's sort of an extension of the word to vec skipgram objective, where you learn a model for, you run a BILSTM over the context or the sentence, and you optimize the representation of this by LSTM so that it can predict the missing word correctly. So what you do is essentially you learn a representation for this sentence, and you try to predict this missing word submitted. And by tying them together with an objective function that's based on like log likelihood, you can embed the word submitted and the entire sentence into the same space. Okay? Yes?
Isn't that exactly the same thing that happens in skipgram? I mean, how is it different?
Skipgram doesn't run, oh, sorry. Skipgram doesn't run any bias. So the way you embed a context into the same space is you run a BILSTM over the context. So you have one representation for the context based on the BILSTM. And then you use that representation to predict the word. Right? So it's an extension of skipgram, but it's not exactly skipgram because skipgram doesn't run does not combine like the context into the same representation. So you use the center word to predict the neighboring words, or in like Seabaum models, you use like the neighboring words to predict the center words, but you don't combine the neighboring words into like a single context.
The representation of the context is the last.
The representation of the context, yeah, it's the last hidden state in the LSTM. So what actually happens is you run an LSTM on the left side of the submitted and an LSTM on the right side of the submitted and put these two together. Okay, so two ways to represent this context. One based on pooling, the other based on RNN composition. And then from there we can, if assuming you have word embeddings that you've already learned, you can get these contextualized word embeddings by doing this dot product, vector multiplication. Okay, so just to briefly recap all the pieces that I have so far, we have a data set for Hypernym E detection. We have a classifier which is built to detect Hypernym E, but it does so in a context agnostic settings where the inputs are word embeddings. And so we transform the input to this by feeding it not word embeddings, but contextualized word embeddings. And we contextualize the word embeddings in these two different ways. All right, so let's just put all these pieces together and see what happens when you apply the classifier to the data set. So I'm going to walk you through the results. The three lines that you see at the top correspond to three different experiments with the pooling model. So the line on the top, the blue line, corresponds to what happens when you feed the classifier an input which is just the word embedding. And so this model does not have any knowledge of context, right? The line below that, the green line, is what happens when you feed it the contextualized word representation, and the yellow line at the bottom is what happens when you feed the model as input both the contextualized word representation and the raw untransformed word representation, which has no knowledge of context. So it sort of puts both of the features from both of these representations together. Okay, so you can do the same thing with the other model, which is the RNN composition model. And I have one more experiment where we do sort of a hybrid model where we combine words from one source and the context from the other source. So the idea is that if both of these are really complementary, you should sort of get the best of both worlds in these two different models. And so we combine words from one source and the context-aware representations from the other source. And so what happens? So the first thing that you see is all models do sort of like better than this trivial all true baseline, which is nice. It's sort of a sanity check that things are working as you expect them to. But that's not really the most interesting thing. The first thing that you see is that the context-aware representations are really weird in the sense that they don't work as well as the context-agnostic representations. So the green lines are worse than the blue lines. But when you put the context-aware representations with the simple word embeddings, the context-agnostic representations, they give you a minor boost above what the blue line is. So the yellow line does better than the blue line. The hybrid model works the best, but unfortunately, the performance of the best model is not really that great. It's not a large improvement over context-agnostic baselines. What we really want is models that use context should do much better than models that don't, but we see that that improvement is really minor. So what exactly is going on here? So we decided to unpack this a bit, and we decided to evaluate our models on a subset of the data set that consists of the positive examples and the permuted negative examples. So what this experiment is going to tell us is how sensitive are the models to changes in context. just focus on like the context sensitivity part. And on this data set, you see that the context-aware representations behave as they should. They do better than the context-agnostic representations. The relative performances of everything are still pretty low, but they do capture what they're intended to. And the hybrid model is like still up there. It's not the best, but it's still better than all the other context-agnostic models. So which begs the question, what happens in the overall model where the context-aware models are not doing well? And to answer this question, we looked at another subset of our data set, which consists of the positive examples and the flipped negative examples. So we are trying to understand if all the models that we are considering capture directionality or asymmetry that's inherent to the task. And when we do that, we see the final piece of the puzzle fall into the place, because we see that the context-aware representations that we are considering really do much worse than these blue lines, which are the context-agnostic representations, or they do just as well as them. So they're not really good at capturing this asymmetric relationship that we're trying to do. And so when you put them together into a bigger picture, you see that the overall performance in the data set is worse. In general, we see that the context-to-vec models seem to be doing better than pooling models, which is it's sort of good news because the RNN models are doing better than the naive composition models. And finally, we again see that the performance on detecting asymmetry is best by the hybrid models, again indicating this complementary source of information that these two models have. Okay, so I'm going to like quickly summarize this part of the talk. So we showed that this particular problem is challenging. Like we still don't have a lot of good models because the models that we have considered have not been quite up to the mark for this task. Although we did show that the context-aware representations that we considered helped in capturing this different sensitivity to context, but they did worse at capturing these asymmetric relationships that we are concerned about. And finally, we showed that if you have hybrid models, they can sort of build better things out of two individual pieces, but still, again, it's not that great. And so just to reiterate what I was talking about earlier, we have a data set, we have some empirical comparisons of different models, and empirical comparisons which show that these models are and are not sensitive to these different things. And so the data for this is available online. You can go and play with it if you are interested in. And it's basically what I'm going to talk about for the first half of the talk. So this would be a good time for questions. Yes?
Yeah, so just wondering, like, why is it not performing better? So is the objective function symmetric by any chance? Like dot product?
So the classifier, so the word embeddings themselves are not symmetric. The classifier that we consider extracts features that are not symmetric. So there's definitely an asymmetric component. So we transform the word embeddings into features, and the features are asymmetric. So they are dot products between, they're not dot products between all possible pairs. Like they're selective dot products, which includes asymmetry into the model.
So like, for example, where the flip is between, where you just flip the label.
Yeah, so that's the data set. That's the subset on which these models do worse. I think like my hypothesis at this point is that the word embeddings themselves are learned using like a symmetric objective at the very bottom, and so it doesn't matter like how good asymmetric features you extract, they're still going to be very much driven by symmetry. So what I'm going to like, what I'm trying to do right now is trying to have a more end-to-end objective where you learn this asymmetry from the start. Any more questions? Yes, so the question is, did I consider the issue of lexical memorization? I did, but since this is different data set than standard lexical entailment data set, there was a split where the training data did not overlap with the test data in terms of the word pairs that we considered. So we made sure like there's no lexical memorization happening. Okay, any more questions? All right, so I'm going to switch to the second half of my talk where I'm going to talk about Hypernym E detection in cross-lingual settings. I'm going to talk about more current work that I'm doing and not the paper that I put up there. And this work is in collaboration with Shyam Upadhyay and Dan Roth from the University of Pennsylvania. So the basic motivation for this problem is that there's a lot of lexical variation in translation. So if you look at the French word apartment and you go to like a large corpus of parallel sentences and training data for machine translation systems, you see that the word apartment is variably translated. It can be translated as home, it can be translated as apartment, it can be translated as studio, and all of these different relationships are not the same. So apartment in English means the same as the French apartment, but the other relationships are more asymmetric. And so the question that we are asking is, can we identify such divergences using Hypernym E detection? All right? And there are various reasons why these divergences can occur. Choice of the translator, maybe things don't translate exactly between the two languages because of the language gap, or various other reasons. But the question is, can we identify such divergences? And so this is a simple example of how Hypernym E looks like in cross-lingual settings. Instead of having the two words in English, you'll have a word in English and a word in French, or whatever other foreign language that you want to consider, and then you have an associated label. So why is this task like sort of challenging than the more standard vanilla Hypernym E detection task? The first reason is that back translation is not really an effective solution. And as an example, consider this setting, where the English word aspirin, which corresponds to the medicine aspirin, implies this French word, which means medicine. But it does not imply this French word, which means drugs, and not the medicinal kind of drugs, but the more narcotics sense of the word. But when you translate, say, one of these two words back into English, it might happen that it's translated to drug. And in English, we conflate these two senses into one word. We have words for medicine, we have words for narcotics, but then we also have a common word which means both. So the question is that if you go from this to this, what exactly are you capturing? So all I want to say is that this translating the pair back to English and then solving the problem is a good approach, but it does not capture variability in language, or even the fact that like we don't even have reliable translation systems, so doing that is really not the good idea. So the question is then, can we solve this problem in a bilingual setting where the two words stay in the two languages in which I've been given? So if it comes to that, then the second challenge is that we need to somehow bridge this language gap. And what I mean by that is most approaches to Hypernym E detection have focused on monolingual settings using models that are built for the same language. So how can we port these models to a more cross-lingual setting where words can occur in different languages? And finally, there's a lack of data sets for evaluating this task. So the work that I mentioned here, which was presented in NACL last year, took a step in this direction. I'm going to quickly summarize it because the current work that I'm going to talk about builds off that work. So the starting point for that work is this idea called the distributional inclusion hypothesis. And just as an example, what I mean here is the more specific word, in this case, Spider-Man, is going to appear in a large text corpus with a bunch of context. It's going to appear with a bunch of surrounding words. On the other hand, the more general word, which is in this case, say, superhero, is also going to appear with a bunch of different words, which are going to be in its context. But the context of the more narrower word, so of the word Spider-Man, are going to be a subset of the context of the word superhero. So what I mean by this is Spider-Man will have some properties which are specific to it, but the word superhero will have some properties which are more general and which sort of subsume the properties of Spider-Man. Okay? So that's the starting point for our model. But this begs two questions in the cross-lingual setting. The first is that how do you represent and compare contexts across languages? The second question is, how can you measure the inclusion part of it? Okay? So to answer the first question, I'm going to describe a model that we proposed. This model is based on a projection of words into different languages into the same vector space. So we represent words in a vector space which is bilingual, which is important. And we also enforce some constraints on this vector space to make it sparse and non-negative. And by doing that, what we end up doing is each dimension will correspond now to a latent but interpretable context, and then we can just compare context across languages. So that's just the description of the model. I'm going to walk you through some of the technicalities. I promise this is the only math on these slides. So the model looks like this. You start with monolingual co-occurrence statistics. So you just build a word context co-occurrence matrix in 2 languages. And then you solve 2 matrix factorization problems. So the matrix on the top is co-occurrence statistics for English. And you solve this matrix factorization problem with L1 penalty, which indicates that we want to enforce sparsity on the final A matrix, which is the final word representations that we care about. So we solve a problem like that in English. We solve a problem like that in French. So we have 2 separate dictionary learning problems here. But that still doesn't tell us how to enforce the bilingual constraint, because these 2 matrices still lie in 2 different spaces. So the A matrix in English and the A matrix for French are still in completely different spaces. And so we tie them together using a term which is a cross-lingual objective, which basically says pull these 2 terms closer together in proportion to a certain cross-lingual signal that we will provide to the model. So the unknowns in this problem are the 2 A's and the 2 D's. The X's are the co-occurrence statistics, and the S is a matrix that I'm just going to describe right now. But any questions on like the basic model formulation? And then of course, like to just make sure you have a good solution and all, you have to enforce some constraints, and then throw this whole thing into an optimizer. This is a very non-convex problem. You can use things like splitting methods or ADMM or whatever your favorite non-convex optimization solver is. But the point is that you can just plug it in and get these A's out. Any questions on the model itself? Okay, so question. Right. So by making like this is work that we have done in cross-lingual settings, but in monolingual settings, there's been like a whole ton of work which shows that adding both sparsity and non-negativity improves. So basically, what you're trying to say is that the negative values in your embeddings corresponds to things that correlate in the opposite direction, and that's not really what you're interested in. So as an example, negative values would capture something like dog is not really a tree, whereas that's not very useful information, right? So by forcing positive values, you increase the correlation between the word and the dimension. So you say things like dog is an animal instead of saying things like dog is not a tree. Okay? Question?
Different languages, word may have not dominant, so maybe they can manage that.
Yeah, so the way we build this S matrix is by taking a dictionary of seed words, where I've given a translation of each word in English with a translation in the foreign language, and then just converting this to a matrix. So this matrix can be many to many, right? So this matrix is going to include all the ambiguity from language that comes. So all we need for this model is basically monolingual co-occurrence statistics and a seed dictionary. Okay? So what you get out of this model is word representations for the words in the 2 languages, and this is what we are going to use as features for our next step, which is basically measuring inclusion between words. And I'm not going to spend a lot of time on this because we are just using building off prior work. What we do is we measure inclusion in an unsupervised way by calculating this scoring function. So this scoring function is like cosine similarity, but except it's meant to deal with asymmetric problems. So this scoring function essentially captures 2 components. One is a symmetric similarity, and the other is a more asymmetric inclusion measure based on average precision. But the real important thing is when you put this scoring function together with the model that we have built, we could show that there were some gains to be had when you compare to other representations or like the translation approach in detecting cross-lingual hypernymy. But what I really want to talk about is not this particular work, but what we are doing here is trying to see what happens when you feed this model different kinds of input. So the input to this model is always some sort of a co-occurrence statistic matrix. And the question is that how do different co-occurrence statistics influence performance on entailment? So what we are going to do is we are going to compare syntactic co-occurrences with window-based co-occurrences. And what this means is when you're looking at window-based co-occurrences, you look at how many times does each word appear appear with its neighbors, and where the neighborhood is defined by just adjacency in terms of positions. Whereas if you're looking at syntactic context, the neighborhood is defined by a dependency tree. And I'm going to give examples to make sure that's clear. But the basic idea is that the dependency contexts are useful in capturing functional similarity. And what I mean by this is they capture more of specific semantic relationships than associations. So going back to all the examples that I gave earlier, it captures things more like chess and game as opposed to chess and checkers. Since the latter one is just an association, while the former is a more functional relationship. And so just to give an example of what I mean by these different contexts, let's say we have this sentence with the given dependency tree, and we're interested in collecting the context for the word traveler. If you're looking at, say, window-based context, you'll just look at the neighboring words of the word. So you have the word traveler, so the context for traveler in a window-based settings are the words tired and the word roamed. If you're looking at the dependency context, there are various ways to extract this information. So the first model is something I call the full dependency context, where you concatenate the different ways in which this word is connected in the dependency tree with the labels that it's using to make these connections. So for example, one of the contexts for the word traveler would be the word roamed with this subject label. The second dependency model that we are considering is something we call joint dependency. So joint dependency not only takes into account the immediate children and the immediate parents of the word that we are interested in, but it also takes into account siblings of the word. So just like adding more information to the dependency model, the label is dropped, but we add the sibling information. And the final information that we are final type of dependency that we are considering is unlabeled dependency, where we just drop the labels. So this is in some way a cheaper version of the full dependency model. Okay? Since we are doing this in cross-lingual settings, there's a very natural question of what happens when you deal with low-resource languages. And the real question is that since dependency tree banks might be scarce for low-resource languages, and it might be harder to obtain those in instead of like just raw monolingual corpora, the question is, can you transfer syntactic knowledge from one language, which is high resource, to a language that's low resource without suffering from performance losses? So what I mean is, just assume French is a low resource language. It's really not, but let's just assume French is a low resource language. You have related languages like Italian, Spanish, and German. So can you train a dependency parser on these three languages and then just transfer that knowledge to French? And the real question is, can you do this without losing performance on the task that you care about? Okay, so the question is cross-lingual entailment robust to such syntactic transfer? So again, to just summarize, we have these different contexts that we are going to try and experiment with. All of this is going to go into how you build these two co-occurrence matrices. And then again, going back to the bigger picture, once you solve this optimization, you're just going to do a scoring where you're going to have scores which indicate whether one word is a hypernym of the other word. So again, just to remind you of the two questions that we are asking in this work. The first question is, are dependency contexts more useful than window contexts for cross-lingual hypernymy? And the second is cross-lingual hypernymy robust to syntactic transfer so that you can work with low-resource languages? So I'm going to show you results here. We experimented with 4 different language pairs. So English Russian, English Chinese, English Arabic, and English French. So our baselines are the window-based models, which are these blue bars. If you look at the full dependency context, it always does better than the window-based context. So what this is telling us that yes, dependency contexts are more reliable even in the cross-lingual setting. If you look at the joint model, it doesn't do as well as the full model, which tells us that the sibling information is less important than the label information. And to really drive that point home, if you look at the unlabeled model, you see a sharp performance drop, in some cases going back below the window-based model baseline. So the key point here is that the label information in the dependency trees is really, really important when you're building good contexts. But the most interesting thing here is what happens when you use the transfer experiment, when you use a delexicalized parser and just do some syntactic transfer from high resource languages to low resource languages. And again, none of these are really low resource languages, but you can pretend that they are low resource languages and not use all the resources that we have for this language and just do the syntactic transfer I mentioned. And very, very interestingly, very interestingly, this gives like a very, very robust performance. In most cases, it is at least as good as the joint model, and in one case, it's actually the best model. And our hypothesis is that this, just by using language information from different languages, you sort of learn a more general model that does better than the individual models themselves. Okay, so questions? Yes. So they are in the same family. So for example, for Russian, we use things like Slovak. I don't remember the exact languages, sorry. But it's just like in the same language family. The caveat is that we are using dependency tree banks for from the UDT project, which doesn't have a lot of different languages. So you're really like forced to work with like the few choices that you have for all the languages. But they're really related languages. Sorry, I'll come to you. Yeah, go ahead.
So in the full setting, like, don't you suffer from sparsity because you are considering the label and the word? And how many times do you get that feature?
So I don't have numbers here, but like we have numbers on like how many times do each of these neighborhood features occur. And it's not as sparse. It's definitely sparser than some of the other models, but it's still it's not like that bad. Yes, I had a question.
I wonder if you could comment on the implications of this result, given that most under-resourced languages are only related to other under-resourced languages.
So yeah, so one thing that we've been thinking about is like how many. So it's really nice work at EMLP this year, which did sort of this distillation along like language paths, where it went from one language to an intermediate language, and then from there to another language. So the question is, can you do something similar here, where you, instead of just transferring between two languages, can you transfer via a bridge of some sort of related languages, where progressively each of these elements of the bridge have more information? But yeah, that's a very good point. And so the natural extension would be to consider such a bridging setting. Questions? Yeah, I mean, that's more or less what I want to say. Just to like summarize what I got from these results, and this is very much a work in progress. We have like more experiments and so on planned. What we are seeing right now is dependency contexts do much better than window contexts for cross-lingual entailment. This was something that was very recently done in monolingual settings as well, but this is the first time we can show this holds for even cross-lingual settings. We also said that more is better, and by more is better, I mean that dropping the labels is usually not a very good idea, and using the labels is probably the best idea. And we also saw that for low resource languages, you can show that this task is robust to syntactic transfer from other languages. Yes?
On the previous slide, is it interesting that that Russian still does better with the unlabeled?
Yeah, so something is like, we need to do more analysis, but you can see that not only is the unlabeled pretty good, but even the DLX model is really, really good. It's better than the window model. So yeah, we need to dig in a bit more and find out like what it is about each of these languages that makes different things work differently. But the overall trends are just more in line with what I said. Okay, and the code for like some of these things is online, especially for the older models. The newer one is just like work in progress. We can go and play around with it as well. Okay, so hopefully I've convinced you that like looking at Hypernym E in like these different settings is valuable and raises different questions that have not been raised in the original vanilla Hypernym E detection scenario. That's all I want to say. I'd like to thank my advisor and other members of CLIP with whom this work was done, and also collaborators from UPenn who are equal contributors for the second half of the talk. And any more questions, and I can take them, but that's all. Questions? Yes.
So we talked about syntactic transfer, but is there something semantic transfer equivalence, if you look at probably word embeddings, if they have like similar positioning in the space, in a monolithic space, you think there could be some kind of a transfer possible?
So that's what we are doing with the whole model, right? So what we are trying to do with this model is start out with like two representations that lie in two different spaces and put the final two representations into the same space. And we are doing that by like sharing this common knowledge from these two languages that we have, that we get from a dictionary. But what we're really trying to do is like just put these two together into the same space.
Yeah, but have you considered using the existing embeddings?
Yeah. So for some of like the older experiments, which I didn't talk about here, we did compare some of the existing embeddings then. So this work was done like end of 2015. So whatever existed then, we did compare against those. But for the specific problem, we just showed that this works much better. But it's a reasonable question to ask: how can you like use syntactic information in these other embedding models? Yes.
Have you been able to do like error analysis with this specific context? Because you enforce these constraints and context and error analysis.
Yeah. We do have some. Sorry.
Yeah.
No. So we have done like very basic error analysis, and we show. So I made this very bold claim, which said that syntactic information is more in line with functional similarity as opposed to just word association. So we've done like some analysis on this, and we show that this basically holds. And since we have interpretable context, we can actually look at what contexts are being activated and so on for each word pair. Yes?
Why would we think that that you could that words from two different languages would like live in the same space? Like for example, there might be a language which is like much richer.
Yeah. So absolutely. So this is a very fundamental assumption that we're making here with this model, which is that you can somehow like put two words from two different languages into the same space. That's not necessary. Although like it also like at the other end, there's also this idea that you can possibly embed a lot of words from these two different languages in the same space. And since we are not like dropping vocabularies from the two languages, we also hope that like some of the idiosyncrasies of each individual language would find themselves in this common embedding space. But yeah, it's totally a fair question to ask. Any more questions?